Right. Okay. So, guys, the next thing that we need to discuss is about the extension headers. I need to reduce this brightness on my. Yeah. Is to discuss the extension headers. So let's go ahead to discuss the extension headers in this regard. So here we want to explain what the extension headers are, and then we need to analyze the advantages that they bring to the system, and then we need to list some examples of these extension headers and how they might have been used. And so we need to discuss how these features might have been implemented in the IPv4 environments. All right. Then we'll analyze some trade-offs as well. Then we can move on. So let's pick that extension headers. Okay. So over here, what are extension headers? So extension headers, they are the key features of IPv6 that add extra information or extra features beyond the main header. So the main header in IPv6 is the next header. We explain that, and that is followed by the extension header. So you'll be looking at what goes in there. So it says that they are optional. They are optional. Of course, they are optional, and that they follow the main IPv6 header. So they follow the main IPv6 header. They are optional. It's either you have an extension header or you can have the payload to follow it. All depends. And you can harness a number of extension headers, and then finally the payload or the data frame will follow it. Okay. And that is what I think. I had a diagram here to explain that aspect to you. I think it's right here. Yes. So the IPv6 header is going to have a next header field. So if the next header field is, let's say, 6, that's what we explained right here. 6, that means that the header which is following is a TCP header. And once it has a TCP header, then of course the payload is going to follow it. Also, if the next header field is 58, and then over a 58 is ICMP, then that means there is an ICMP header version 6 that follows it, and then the ICMP payload is going to follow. Similarly, we can have a next header field which points to 43, and then 43 here is one of the extension headers that we have. And as an extension header, then that means that the extension header is a routing header, source routing header. So you're going to have a source routing header that follows, and a source header can also point to has a next header because it's also 40 byte in frame. So which can point to a next header field, which is we could have a protocol, any protocol number as well. So that is how it works in chains. So if this is 6, that means that that's a TCP header that follows. So you can continue and continue like that. You just need to understand how the headers all look like. Okay. So back to the document 2. Okay, so they follow the next header field, which identifies the protocol in the packet's data field, and if extension headers are present. So a packet can have 0, one or more extension headers. That is what I'm explaining right here. It can have a 0, one or more extension, and each containing its own next header. So each extension header will have its own next header field, which is going to point to what is the next field that it follows. Okay, like whether another extension header follows or you are hitting at the end of it where you're going to have the actual payload that follows it. All right. So the last one is going to be, there is also a no next header field that does not include a subsequent protocol or like that. So it all depends. And if you talk about the advantage of having extension header fields, it all boils down to extra key features that have been built into IPv6. Those are the advantages that extension header fields are bringing. So extension header fields in IP, they enhance the protocol adaptability and efficiency by allowing additional features. So the key things about additional features, which we already started talking about ICM version 6, we talked about the fragmentation, we talked about the routing header, and then all those kind of stuff without altering the main header. So the key thing is that you are adding additional features while you do not alter the main header, and that makes it to remain a fixed byte of 40, which for easier processing, we've talked about that, and that they are optional, they're reducing overhead by being included only when necessary. And this header supports multiple protocols we talked about via the next header field, which will point. So every extension header is going to have its own next header field, which is going to point to the next thing. For example, if the goal at layer 3 is to improve security mechanisms, then we can use the authentication header field and then the security payload ESP fields to support this. If the goal is to support fragmentation at the source layer, we could definitely introduce the fragmentation extension header field. TLV's options are very key. They're used in source routing as well. So TLVs will help you to do necessary programmability into the frame. Options enable structured inclusion of all additional information, collectively contributing to better performance and security in IPv6. So that's the goal of TLV. If then we are also asked to give examples of the extension headers. So one of them is the hop by hop option. The hop by hop option, the key thing about it is, unlike IPv4 where all the routers on the routes will have to look through this header, the hop by hop option, and then read the packet to work on it. The hop by hop option here is examined only by routers that are allowed to do that, or that needs to do that kind of information. So it kind of allows reduce the kind of burden that counts for all routers on the path. So this header carries optional information that must be examined by every router along the packet's path. So every router along the packet path, I think we will hit there. It can be used for features like routing information, special handling instructions, so like the flow control and other options that need to be processed at each hop. So the hop by hop, okay, so it does processed by each hop, and it might include options for network performance monitoring or specific routing instructions that need to be considered by all. And then we have the routing header used for source routing. I think the protocol is 43. Yes. Let's go here. Okay, it's not here. It's rather in the PPT here. So, yep. So 43. Yes, that's the routing header. So if you point to routing header, then it's saying that the routing header is this header is used for source routing. Okay, source routing, and then the concept of segment routing is all based on this source routing, allowing the sender to specify the list of intermediate nodes that a packet should traverse. So specify a list of intermediate nodes that a packet should traverse. Source routing is something that is in IPv4, but it's done in a very complicated way. But in here, in IPv6, is simplified in the IPv6 extension headers. So a network administrator might use this to direct packets through specific routers for testing, and then to avoid certain paths due to known issues. And this is also a feature that the central controllers also work with. So software defined networking rely extensively on this routing header for network slicing, and that's where the controller is able to calculate the path that the packet should use. And we have the fragmentation header. This header is used for packet fragmentation and reassembling. In IPv6, we're saying that fragmentation is handled only at the source node, and that fragment will contain the necessary information for reassembly. Examples: if a packet exceeds the maximum transmit units of a segment, the source can fragment the packet and use this header to ensure it is reassembled correctly. So the fragmentation header will help it to reassemble correctly at the destination. Okay. Then the authentication header, I think protocol number 56 or something. This header provides authentication integrity for the packet. It ensures that the data does not or is not altered in transit. So it's all about authentication and integrity. That is age. We have configured age before. It might be used to secure communication, such as VPN tunneling and all that. The encapsulation is all about confidentiality and authentication at that layer. Okay, of the payload. Normally, this we put this one on the payload aspect of it. So that is that. Okay, then the destination options used. So this header carries optional information intended only for the final destination of the packet. It can include options that the destination node needs to process. It might be used to convey information about the expected response or to provide additional configuration parameters for the destination node. Okay, so that is this aspect of its ESPN. That so the next header value is the next header values that will point, we have it all here. Then the kind of extension headers that it brings up to, we also have it here, and whether the extension headers file size. So and then also in terms of support for TLVs and then what it's supposed to do. So that is about the extension headers. So in a summary, if you ask what are the extension headers, they are built-in features into the IPv6 to allow for more additional capabilities. The advantage they bring is that they bring in additional features such as hop by hop options, fragmentation in a certain angle based on source routing. They look at source routing in terms of the routing headers. We talked about authentication headers to build in security and encapsulation, and that's all. You'll be fine. How were these implemented? So hop by hop options in IPv4 includes what's included in the option field in its header, which can carry various types of information that routers may need to process. However, all routers must examine. So this was the point I was bringing, that in the hop by hop in IPv6, only specific routers could allow to do it. You don't necessarily need to. That all routers must examine this field, which can lead to inefficiency and increasing complexity, processing time complexities. So the variable length of the option field can complicate the packet processing and lead to fragmentation, as the header size can change based on the options included. So if you implement a hop by hop, added to complexities of the network, and then this is not happening in IPv6. Then in terms of routing header, yeah, IPv4 implementation, source routing IPv4 was achieved, and it used a record route and the strict source routing options in the option fields. And this option field allowed the sender to specify a path through the network. The limitation is still presented at levels of complexity of how it was done. Processing, and as I told you, IPv6 relies extensively on the lessons that were learned in IPv4 to ensure that those lessons learned do not happen again in IPv6. So in terms of potential issues in terms of routing, they have security, but this time your source driver, you are fully protected using the IPsec tunnels. um Fragmentation IPv4 was handled by all routers along the path using fields such as the application, the flags, and the fragmentation offsets in IP4. Packets were fragmented along the routes, and that kind of haphazard way. So routers-based fragmentation can lead to inefficiency and increased overhead, which router must manage or tend to avoid. So age, IPv4 didn't have the built-in feature for authentication integrity. In other words, you had to rely on the upper layer protocols like the transport layer to provide this level, and this is different in this scenario. So the approach can lead to redundancy as multiple layers may implement their own checksums. And however, that they wanted to have implemented the IPsec in IPv4, and the destination options here, destination options in IPv4 can also be included in the option field, but they are limited in scope and flexibility compared to IPv6 tend to provide us more granularity. So hop by hop options in IPv4 that we're saying that where the option fails to carry various information for the routers, but all routers must examine it, leading to inefficiency in the IPv4 and increased processing time due to its variable length. And it could actually complicate things. Source routing IPv4 is another complication that came around. Fragmentation is at another level of complication. These are lessons that it lacks the built-in thing at the layer 3, and destinations in IPv4 limited had a limited compared to dedicated extension options header in IPv6, leading to increased complexity and potential fragmentation due to variable header size. So that does it for the questions related to the extension headers in IPv6. Let us move, and then I think we can pick the next question. Hopefully I can be able to for okay. So here we want to look at the idea of auto configuration, link local address, stateless and stateful configuration. I have a very specific video on the idea of how Slack works and how packets are actually exchanged using the neighbor discovery protocols. You can check that up on my YouTube page. But then when we talk about stateless address auto configuration, saying that a device uses this information in an array message for all of its addressing needs, including using the prefix. So the array will providing the prefix to create the IPv6 global unicast address for exchange, and we do understand how they able to use their link local address to begin the neighbor solicitation messages, and after that an array message is sent across that contains the prefix for him to use is either is EOI64 or some level of randomness to generate for the client to generate its own global unicast address. So device will use the source IPv6 in the array as their default gateway. Method 1 is the default in, well, that is it. And also in terms of Slack, this is something that I was also giving to you to give you more ideas about the difference between them, and you'll find that difference right here, that when we talk about Slack, they are in the packet header. There is an A bit, there is an O bit, there is an M bit. So when the A bit is set to 1, then in the array message, then it's actually means that it's Slack, and in that case, the interface, the array message will also provided a DNS IP. He doesn't need to have a DHCP server or any additional information. Then for stateless is both Slack, and then you have the option bits also set within the packet frame for the array message. Okay, so in there, what you're going to say is that it's going to set the A to 1, and then the O say give you additional information that even though I'm providing the prefix, for additional information, do talk to a DHCP server. So the additional information could be a DNS record, the NTP, other configurations not necessarily related to the IP, not but in a stateful, you have both other and then the M bits, which is set to 1. And that is where for even the IP and then the DHCP, it has to talk to a stateful DHCP server for such information. And there we've also explained what slag is, that the link local address will generate a link local address. It does duplicate address detection to ensure that nobody's using the IP. If somebody is using it, has to drop and generate a new link local address. Then the device will send router solicitation message to the router. Router will respond with router advertisement, and then we'll set the A bit to 1. We did explain this. So in the array message, the A bit is set to 1, and then based on that, the device configures global unicast address using the prefix that the array provides, and then in the DNS information is also in the array message. Then device checks for DAD. Then we have the stateless, where it still start with the link local address, generates do a duplicate address detection. Device will send a router solicitation. Router will have to respond with the A bits, and then the O bits also set to, that's the O bits also set to 1 for slag and additional information. Global address devices. Device configures global address using slag. DHCP version 6 info request. Device request additional config from the DHCP v6, and then DHCP basically will reply the message. So in here, there is basically no slag information involved in this scenario. Is fully DHCP packets that you are going to see across, and I have captured a copy. Oh, sorry for this. I got it. Strange. So here is fully DHCP packet that you are actually going to see that will be going across, and the server offers the IP address, and then request and reply. Eyes are closing. Have mercy on me. So that's. So let's go back right here, and then we can draw some very meaningful conclusions about this. So Slack is stated as similar to the method in 1, the device using Slack to create a global unicast address, whilst it's for additional information, it uses the DHCP server to request. So it's going to have the O bit also set to 1, such as the DNS server IP address and any other information. So the array message doesn't specify what information is available in the stellate DHCP. It will just reference the host to talk to a DHCP server to get all those kind of stuff that it requires. Okay. Yeah, it could be a DHCP version 4 server, it doesn't really matter. But a DHCP version 6 server is fully providing DHCP version 6 services, in addition to providing the DNS records and then all those kind of information. That is for the stateful. Link local address, we're saying that is not routable. It's only located on the link. The link address is linked this, and then it's not routable subnet. And then link local addresses tend to be the next hop when it comes to IPv6. So when you are sending the traffic out of the LAN, it's going to use the link local address as the next hop by default. That's what it's going to do. Okay. So I think roughly I have exhausted this part. I'll pause here, and then the next requirement will be for us to discuss the business case in this scenario. So we've discussed this aspect. So in terms of configuration wise, list the capabilities of IPv6 analysis and examine the business case of IPv6. So we'll look at it, and we're basically going to continue. Thank you.